Okay, so we will start the session now. I think so. We have waited for some time, and people will come and go. Okay. So I welcome everyone to this SciChat, and it is a series of SciChat. First of the series. Basically, we are starting with physics. So Nobel Prize in Physics. We will be discussing the topic, the Nobel laureates, and plus we'll start from the basics so all the lay people can get to understand it, and we will go see how much we go in advanced levels. Okay. So we have with us today Dr. Madhusudan P. He is a postdoc fellow here at Physical Research Laboratory from Ahmedabad, India. He has done his master's in Mysore in physics from Mysore University, and he has done his PhD from Physical Research Laboratory itself. And he has another postdoc coming up from Center of Atomic Energy at France. I think so, right, Madhu?
Yeah, University of Saclay.
Yes. So from France, and one of the Nobel laureates from physics this time is from this institute itself. So I think so he is the right person to give us the arena of how and why the Nobel Prize was given to this thing. Okay. So Madhu, I would like to first of all start by asking you about yourself, how you got interested in this field and how you started off with your research and how was your PhD thesis doing. So,
okay. Before I get on to that, a couple of clarifications.
Yes.
Two of the Nobel laureates were from University de Saclay.
Wow.
Both Anne Houllier and the guy who got the rabbit spectrometer.
Yes.
So both they did their attosecond research over there.
Yes.
And so that was the thing that I want to say. I don't know if I'm the perfect person to speak about this. It's just that I am in this field, so I have little knowledge of what they are doing.
Yes.
So we can get to that. And yeah, so coming back to me, how I got into physics or anything. See, I am from Bangalore. So if you know Bangalore, it's the city of IT. So many people expected me to go pursue engineering in my 12th, but since 12th, I was inclined towards research. So this curiosity has always driven me, even in my master's or bachelor's. There were opportunities for me to shift to IT if I wanted to engineering, but I was not interested. So even in my masters, when they asked me why did you choose MSc Physics, the only answer that I had was, don't give me masters, just let me sit in the classes. So I was only interested in the classes, whatever it was. Even here I got a wonderful opportunity at PRL, the lab that I'm working in, femtosecond laser laboratory. I was very fortunate enough to see this laboratory from scratch. And we have some of the world-renowned spectrometers here, and probably the only place that I can see that I know of which has multiple spectrometers and the laser facility that we have right now. So this lab is the cutting-edge lab in my area of research. Therefore, I'm very fortunate to be in PRL, and this has been my life. So even in my lab, I try very interesting or rather non-intuitive things, which I'll be talking in the later chat as well. So this has been my life until now. So yes, the postdoc, I am an internal postdoc here, so I would be taking up my second postdoc at University Paris.
Yes, great. Yeah. So tell us something about your research, Madhu. What you have done as a PhD fellow over at PRL.
So for me, light matter interactions was very fascinating. Therefore, in studying light matter interactions, I studied them at a time scale which is inconceivable. At least for me, when I joined the field, it was inconceivable. So I have studied attosecond changes in electron dynamics using femtosecond laser pulses. Put it very briefly.
Yes.
So this is a unique sort of a research wherein you use a larger scale pulses to measure something very small, which is very counterintuitive. But luckily, with the support that I had in my team and with my supervisor, I was able to do this. Majorly, I studied molecular interactions, like how the molecule dissociates, yeah, how the molecule ionizes in the presence.
Basically, how the molecules break apart and then join.
Yeah, fragmentation basically means the breaking up of molecules. So how, for example, if you consider a CO2 molecule or a CO molecule, what are the fragments that it is going to make up? So that was my interest. So that is what I have studied in my PhD.
Yes, great. So let us start with the basic of the field. I mean, what are lasers? Because lasers have always been a fascination for everybody. I mean, for normal people, lay people also, for research also. It has been used across all the fields like biology, physics, chemistry, everywhere, and it has been a source of constant Nobel prizes. Yeah. So,
right.
Yeah.
This is actually very true since Albert Einstein in 1905, when he gave the theory of photoelectric effect, to the latest 2023 Nobel Prize for Agostini, Hulier, and Franz Krauss. So lasers have been at the pivotal point of all modern technologies. So even when photoelectric effect was identified or photoelectric effect was discovered and was suggested by Einstein, nobody had thought such a thing can happen. Similarly, when I want to jump almost 100 years, when Ahmed Zuhail suggested his femtochemistry, even that was a revolutionary topic. Further in 2017, when Donna Strickland got her Nobel Prize for chirp pulse amplification, this has been a field wherein a lot of Nobel Prizes have been awarded to. Like, if you look at why this is happening, you see the importance of laser in your everyday life. You put a CD into the computer, a laser reads it. You want a car, a laser has joined the bolts and everything. You need something cut, you have a laser fabrication facility where you do it. You want some sort of removal or some sort of biological surgery you needed, lasers were used there. So lasers have been pivotal in everyday life. Therefore, to get back to the basics of what a laser is, I'm sure everybody knows what a laser is. Basically, it's a single wavelength which is of multiple photons. The intensity is so high and of a single wavelength. This was the ideal definition of a laser. But then when pulse lasers were introduced, the definition sort of deviated from it. But for now, you can consider it is a coherent beam of light. So, monochromatic beam of light.
Yes, correct. So the lasers have been in use for so long, but one of the most intuitive aspect of laser has been its interaction with matter. And all fields like welding, cutting, everything, there is interaction of laser with matter. So to study such laser matter interaction is very important. So I would like to ask you that what is the meaning of this laser matter interactions? And you have basically studied the interaction of laser with gases. So please speak something about that also.
I mean, it is very evident that our life wouldn't be what it is if there was no laser matter interactions, or rather, more basically, light matter interactions.
Light matter interactions.
So light is of different wavelengths. You go from X-rays to gamma rays. Everything is light, or IR, whatever it is. Everything is light. So even from the perceiving of an object, which is your vision, to photosynthesis in plants, wherein you have different molecules coming together to make the food of a plant. Even there is light. Without light, it is not possible to study anything. Therefore, light matter interactions was very essential, and that was the topic that I chose for my research as well. So these light matter interactions scale from the minute microbial interactions, molecular fragmentations, to the collisions of galaxies, black hole, and everywhere. So this was the importance of light matter interaction. So if you see light matter interaction, even as I said, photosynthesis. So even that was a crucial field. Even this area of research, the femtosecond chemistry or the attosecond chemistry, are more interested in how photosynthesis happens or
Yes.
further things.
Yes, there are a lot of biology people here, so that
Sure.
makes a lot of interest in them.
Right.
Photosynthesis. Yeah, that is that. Okay. So basically, laser matter interactions are possible with normal lasers also, like the pointer laser also. But to see the effect, we need some very powerful or high intensity lasers, or to say we need pulse laser also. So I need you to tell me what are these continuous wave lasers or pulse lasers, until what scale have we come down to, like micro, milli, nano,
Okay.
femto, pico.
So let me first say that if we have a high photon energy continuous laser or a short laser of X-rays or UV rays, we would be very happy. But since that is not the case, we can't bring down the wavelength. We have explored our way into pulsed lasers.
Yes.
So there are two types of lasers, wherein let me start with continuous lasers and pulsed lasers. Yes. Continuous lasers is wherein the wavelength is always constant, the amplitude is always constant. But in amplitude, as in the power of the laser is always constant. While in a pulsed laser, there are blips. There is shoots. There are shots of power that happens. So this is the fundamental of a pulsed laser. Now, let me talk about the. I think you're asking me about the time scales of it.
Yes.
So why are pulsed lasers important?
Yes.
So see, let's say you have a headache. You take a tablet. It takes 6 hours to affect your headache, or maybe 3 hours if you have a very good tablet. Then this is known as the time of rate of reaction. Your action was your headache, and you took a tablet. It took 3 hours to mitigate this problem. So that was the rate of the time, the rate of reaction.
How much time it takes to react with the things in our head.
Right. So similarly, if you consider a computer, the electronics that are working, it is in the order of nanoseconds. Yes. The electrons will trigger the transistors in the order of nanoseconds.
Yes.
Now let's go a little deeper, which is picoseconds. Picoseconds is 10 power minus 12 seconds. So in the order of picoseconds, any molecule that is there, it will take one rotation. Yes. Probably most of us have studied the rotation of a molecule, wherein the vibrational energy levels are all involved. The time scale of this is in the order of picosecond. Okay. Now, let us consider this molecule, let us fix this, and let us break the bonds. If you want to break the bonds, this process happens in the scale of femtoseconds. Now, consider only one atom and see how the electron moves. The time scale of the electron's motion is of the order of attoseconds. Now, if you want to go to sub-attoseconds, which are zeptoseconds, that is 10 power minus 21 seconds. So an electron, the light traveling from one end of the hydrogen atom to another end of the hydrogen atom is of the order of zeptoseconds. Or the nucleus that is involved, the proton or neutron interactions, that happens in the order of zeptoseconds. So these are the time scales in which I want to classify the pulses. So if you want to measure something like the bond breakage of a protein, bond breakage of a chlorophyll or some biological compound, you would want to study that in the frame of femtoseconds. But let's say you want to see the charge transfer that is happening in a protein from one end to another end, or charge transfer in a molecule, that you need to study in the scale of attoseconds. Because if you go to the femtosecond regime, the electron cloud which was on the one atom or one molecule would have already moved to the other end. Therefore, these are the different scales, and for each it is if you want, it depends on what you want to study. So that would define which scale you're choosing.
Yes, but why would we need? I mean, मान लो मेरे को कुछ femtosecond scale पे study करना है. Why would I need a femtosecond pulse of laser? ऐसा क्यों?
Okay, it is as simply like if you have a millimeter sized object, if I want to measure the size of this pen, if I use a meter scale which has a least count of 1 meter, I wouldn't get accurate measurement of this.
Yes.
So what would I use? I would use a small 15 centimeter
15
scale
centimeter
to measure this. So we need the scale to be of the same order of that of the thing that we are measuring. And here the thing that we were measuring were reactions.
Yes.
Be it molecular reactions or electron reactions, they are of the same scale of which the pulses that we should be using.
Correct. Okay, so actually I think so let us give some intuitions to the audience. You know, अभी उनको ये femto, nano, atto इतना मतलब हाँ छोटा छोटा time scale है, but कितना छोटा है, that is more important I think so that they understand.
Okay,
तो
I have
तुम लोगों को कुछ उसका intuition दे सकते हो कितना छोटा है ये?
Right, I have a good analogy for this.
Yes.
So in 1 second, there are as many or there are more attoseconds compared to the birth of the universe and number of seconds. So it is like, let me clarify it. So in 14.7 billion years that we think the birth of the universe
Age of the universe, yes.
Age of the universe. Number of seconds in that lifetime is almost equal to number of attoseconds in 1 second. So attoseconds is so minutely small. If you lived in the scale of attoseconds, you wouldn't even see 1 second.
Yes, correct.
Throughout the universe wouldn't see 1 second.
Yes, that is such a minute, such a small amount that we are.
You see, the fact is you don't even see electrons. You just can measure the position. You just predict the position. Now I'm telling you, there is some field which will affect the motion of an electron or the time scale at which the electron is rotating. It is that fundamental. This is the definition of fundamental science.
Yes, this is really small. I mean, I work at double the time scale that you are working. I work at nanosecond level. और उससे भी, I mean, 10⁻⁹ और पीछे जाना है, 10⁻�18 पे जाना है. I mean, बाप रे.
Right. It's not actually double.
Double नहीं है.
Orders. 10⁻⁹ orders.
और पीछे जाना. 1 billion orders और पीछे जाना है, और तब जाके सेकंड मिलता है. I mean, it is such a small time scale जहाँ पे आप काम करते हो. But
right.
भी ऐसा बोले कि जैसे स्केल हमको चाहिए, we need a scale, a 15 centimeter scale to measure length of the pen, right? आपने example दिया. But what you said in your thesis, basically you are telling me that आपने femtosecond scale use करके आपने attosecond electron का dynamics measure किया है. तो आप अपने आप
I am contradicting myself.
Yes.
But the thing is, see, if you have, I lied a little bit. So when I said the femtosecond pulse, it is the envelope of the pulse, but inside that is traveling is an 800 nanometer wave. Okay. So I employ this 800 nanometer wave and another 400 nanometer wave to do my bidding. But the oscillation of this 800 nanometer wave is of the order of 2.3 femtoseconds, like in some femtosecond range. And 400 is even lesser. Therefore, I cheat away into physics, saying that I'm using a femtosecond pulse, but the carrier pulse is already an 800 nanometer pulse. Okay, so I use the
pulse है, femtosecond pulse है, उसके अंदर भी कुछ jiggling होता है. There is some photons that are vibrating at even lower time scale.
Right. So for example, if my hand is the pulse, so each finger is the different carrier frequency.
Yes.
So this is the 800 nanometer frequency.
तो आप किसी एक finger को use कर लेते हो उसमें.
Yes. So what I do is I take two overlaps, and wherever there is a shoot in the overlap, I pick that up and I study the reactions.
Yes, very good. अभी थोड़ा सा हम एटोसेकंड पे आने से पहले थोड़ा सा फेम्टोसेकंड डिस्कस कर लेते हैं. तो उसका क्या इंपॉर्टेंस है? मतलब उसको भी नोबेल मिला है, राइट? इन 2018 it has also got the Nobel. So what is its importance? Femtosecond pulses, उसका थोड़ा
So let me tell you why we got the Nobel Prize for that. It wasn't actually for detecting femtosecond pulses, but it was actually for amplification of the femtosecond pulses. So what happens in a pulse is you have, let's say, 100 units of energy. If it is a continuous, this 100 is divided uniformly. But if it's a femtosecond, this 100 units of energy is compressed into 10 power minus 50 seconds. Therefore, there is a huge shoot in the power of the pulse. Therefore, the peak power. Right. This is called the peak power. Yeah. When you divide the total power of the pulse divided by the time scale of the pulse, that is a peak power of the pulse. So this peak power is very high. Therefore, amplification of this was very difficult. While Donna Strickland and Gerard Moreau, who got the Nobel Prize, they were so clever enough that they said, why should I take a femtosecond pulse? I'm going to stretch the pulse so that my devices or my optical devices won't get damaged. So he stretched the pulse. Now peak power came down. Now he amplified this low energy pulse. He multiplied this pulse multiple times. And then he compressed the pulse again. So this was a very, very cute, very ingenious trick wherein they used, this is actually called chirped pulse amplification. So in our field, we are majorly straightforward in saying that this is this is two color interaction, this is here. So in our field, chirp means changing the time scale of the pulse. A positive chirp and a negative chirp. So this was called chirped pulse.
फिर अपना प्रोसेस कर देना एम्प्लीफिकेशन और फिर से छोटा कर देने का.
Right. So in this way, we were able to save most of the optics. If we tried to amplify without doing this, our optics would burn. Our optics have burned.
Yes, of course.
Yeah. So most of the things that I'm telling you right now is in some way we have experienced this in our lab.
Yes, correct. True. So basically, if any audience wants to ask the question, they can ask. Right, हमको बीच में भी interrupt कर सकते हो. You can write it in the chat also. So I can just take up the questions from chat, or you can on your camera unmute yourself and ask also. No problem. Okay. So does anybody have a question before I move on to the next question? Okay then, so I will ask my next question. तो चलो ये femtosecond ठीक है, चलो femtosecond तक गए, it's okay. We went till the femtosecond. Why go further down to attosecond? Why is it so important?
We are not happy with our research, so we go deeper. That is my direct answer. So let's see. Let's see. Now we have understood how the molecules fragment. Now we want to see how the electron was responsible for this fragmentation, or what is happening to those electrons. This is very straightforward in a small molecule, but biology people would know that proteins are a huge chain, or any other biological compound is a huge chain. There, if a positive charge or a negative charge is traveling from one active site to another active site, we want to know what is the path that they are taking. Therefore, if we are interested, we could intercept this path. This is the fundamental, or I would say, long-range interest of our community. Basically, to identify these pathways in which it is going. Now, I told you that there is a charge that is migrating. This charge migration is happening in the order of attoseconds. Therefore, to study this, we came into something called attosecond science.
Okay.
So, yes, this is why we want to do attosecond science in the first place.
Okay. तो उसको detect कैसे करते हैं? I mean, attosecond, such a small scale. How do you detect such a small scale at a lab?
Let me tell you a story. Before getting to this attoseconds, there is something called higher harmonic generation.
Okay.
Now, I was saying 800 nanometer pulse, 2.3 femtosecond. इसका मतलब क्या है? एक पल्स है, उसका एक क्रेस्ट और दूसरे क्रेस्ट के बीच में, if you take it in time scales, it is in the order of femtoseconds. Now, I'm telling you, let's go to attoseconds. I can't take this pulse, go to attoseconds, because एक pulse तो होना चाहिए. For that you go to higher frequency, lower wavelength, higher frequency. Therefore you go to higher harmonics. So 800 ka it's the second harmonic of 800 is called 400. 800 divided by 2. Then third harmonic is 800 divided by 3, which is 266. Similarly, you go to the scale wherein it is 100 nanometer to 1 nanometer. In this short scale, you are producing pulses. So now you have the wavelength now. ठीक है, ये wavelength मिल गया. Now you want to compress the pulse, or you want a short pulse to be there. How do? You tweak some of the parameters and you bring that attosecond. Now the second problem is you have generated such a short pulse, but you don't have a scale to measure it. How are you going to do it? So now what you do? You make your own scale. You make a detector to measure that short pulses.
Okay.
So that is where Agostini would shine here. He suggested a pulse measurement technique which is called rabbit. So another interesting thing is our field, we are very obsessed with small animals. We name all our pulse recognition techniques in terms of animals. We have a frog which is used for femtosecond measurements. We have spider for femtosecond measurements.
Spider is in our lab also, right?
Yes, we have one spider and we have one frog in a grinole in our lab.
In a clean room.
Yeah, in a clean room. And we have a grinole. Grinole is the French word for frog.
Yeah.
Then we have a frog crab to measure attosecond. We have rabbit to measure attosecond. So we are very obsessed with this. But coming back to rabbit, the Agostini's contribution.
Yes.
So this rabbit was so phenomenal at that time. We were able to measure the attoseconds, the pulse duration of these pulses. So it was very interesting for us. So getting into the physics of how this happens I think is very extensive. Yes. But Agostini's paper is very enlightening. If you read it once, I'm sure you're going to have some idea about it.
ऐसे जो पेपर लिखते हैं ना, उसमें मजा आता है. Anybody can understand it.
And they get Nobel prizes.
Yes, that is true. That is so true. So yeah, we have come now to the Nobel Prize section. क्यों Nobel मिला, कैसे मिला? Okay. So how do we generate this attosecond? We know now how to detect it, because सबसे पहले तो detection आना चाहिए. We should know how do we detect such things, क्योंकि बना लिया फिर पता कैसे चलेगा कि भाई बन गया है ऐसा.
Yeah, but real life rarely takes that route.
Yes.
In real life, you first generate it, you don't know what is happening, then you design a technique to measure this.
Yes.
So the way of generating attosecond pulses is called higher harmonic generation.
Okay.
So my colleague Pranav, he is an expert in higher harmonic generation. So basically what we do is we take whatever femtosecond pulse we have. For now, in our lab, we have an 800 nanometer central wavelength femtosecond pulse, which is at 26 femtoseconds. We take this pulse and we focus it onto a cloud of gas. What happens when we focus it onto a cloud of gas? The electron which is there, the electric field by the laser is so high that the electron can just tunnel out. It is not even ionization. It is not even going to a higher energy level or coming out. It is tunneling out of the potential barrier.
Okay. And can you just simplify a little this potential barrier and quantum tunneling? Thoda sa.
Okay. Quantum tunneling is a very interesting but a very complicated topic. It is like if you have a barrier and an electron can pass through this barrier without without major changes. That is called tunneling. So क्या होता है when the electric field is very high of the laser, उसका जो potential energy curves ऐसे था वो twist हो जाएगा, वो bend हो जाएगा, जिसकी वजह से एक दीवार जैसे बन जाएगा. तो ये electron it passes through this quantum barrier through something called tunneling.
Okay.
So ये electron अभी बाहर आ गया. Now free space में है.
Now it is in free space. Yeah.
अभी भी electromagnetic field है. therefore it should follow the electromagnetic field lines.
Okay.
So वो बाहर जाके वापस आके टकराएगा.
Okay, so basically electron gets out, it tunnels out, it is still in the electric field of the attosecond pulse, so it will ricochet back, come
Yes.
back again. So
Right.
क्या होता है?
तो ये जो टाइम स्केल है ना, जो रिकोशे बोला है, इट इज एक्चुअली टर्निंग बैक ऑफ एन इलेक्ट्रॉन. So it goes out and comes back. This time scale is of the order of attoseconds.
Okay.
So ये attosecond तक उसने एनर्जी लिया electromagnetic field से, फिर वापस आके it hit back the atom. Therefore it gives out a pulse which is in the order of attoseconds. And the energy of this pulse is directly dependent on how much energy this electron has taken in. In our institute, we have done simulations for this as well. From scratch, we have seen how the electron goes out in different forms of field. So, अगर दो field है तो कैसे होगा? If you have two fields of different polarizations, कैसे होगा? We have seen this in our lab, in our simulations, and we have reciprocated them in our experiments as well. So, coming back to how an attosecond pulse is generated, this is the theory of higher harmonic generation. Tunneling. The second is reacceleration. The third is recombination. So this is actually called the three-step model. So actually, to quote Neil deGrasse Tyson, we physicists use very simple terms. 3 steps hai to wo 3-step model ban gaya. So in this way, this is the higher harmonic generation ka principle. So with this, you generate higher harmonics. Pulse trains bolte hain usko. Now by controlling the गैस प्रेशर, ये जो इलेक्ट्रॉन क्लाउड है उसका प्रेशर कंट्रोल करने से, या फोकसिंग ज्योमेट्री और द पोलराइजेशन ऑफ द एटम, ये सब कंसिडर करके हम उस ट्रेन्स को वी कैन फेज मैच देम एंड गेट attosecond pulses.
Okay. And what are the energy ranges of this attosecond pulses? I mean, वो पीछे आके टकराया, फिर वो attosecond निकला. Okay, but energy कितना रहता है? Is the energy less? Is the energy sufficient for your studies?
So let's see. Hydrogen needs 13.3 electron volts. ये तो 12th standard physics है. Now we have 800 nanometer pulse in our lab.
Yes.
800 nanometer. I'm going to give you this. It is 1.6 eV.
Okay.
So just 800 is not sufficient.
Okay.
That is why there is a different process that happens to ionize this hydrogen. Let's consider hydrogen. To ionize this hydrogen, we need more energy. Now let's go to XUV.
Yes.
Extreme ultraviolet.
So that is actually the very end of the ultraviolet range.
Yes. So higher harmonic generation. From higher harmonic generation, you produce XUV pulses. UV or XUV pulses.
So what is the wavelength of this XUV pulses? Range क्या रहता है?
100 nanometer to 1 nanometer. XUV का और भी short होता है, but VUV and UV pulses से नीचे, मतलब 100 to 1 nanometer. 100. Now, if 800 nanometer, I'll tell you a simple calculation. मुझे पता है 800 nanometer, it is 1.6 eV. So for 80 nanometer, it is 16 eV.
Okay.
So for 8 nanometer, it is 160 eV. So 160 eV is the energy of the photon. Now you tell me, is 160 eV sufficient to ionize hydrogen or not?
It is, of course.
Of course.
Yes.
So these higher harmonics are very efficient in ionizing the molecule. That's why I said, you give me a source of shorter time scale, like 100 nanometer का femtosecond laser भी दे दे, मैं बहुत खुश रहूँगा. But in reality, that is not the case. That is why we still go with Ti-sapphire crystals.
Yes, that is great. That is great. So yes, okay. Attosecond कैसे generate होता है वो हमें पता लगा लिया. But why? मतलब ये Nobel Prize इन ही 3 laureates को क्यों दिया गया? Why the Nobel Prize to these 3 people, Pierre Agostini and Louis Lear, Ferenc Krauss? Why? क्या इनका contribution है?
इनका contribution is they have studied many interactions in the order of attoseconds. ये तो तीनों ने किया है. But on top of that, Agostini and Hulier, they have given theories of how this is happening. And they have been responsible for the experiments. Not exactly theorists. They mostly are experimentalists. Agostini, तो he has developed this technique to
ये
measure
मॉडल
something.
ये 3 स्टेप वाला जो था वो उन्होंने किया है?
No. Actually, in our area of research, this is a very controversial topic. ये जो 3-step model है, that was given by Paul Corkum. He's a physicist in Canada. Okay. Many of the people in our community believe Paul Corkum should also have been one of the person in the Nobel Prize.
Yes.
Yeah, but I don't want to comment on why it happened or what happened. Let's get back to why these 3 people got.
Yes.
So they made fundamental contributions to attosecond science, be it measurement, be it theory of how attosecond pulse train is formed, or be it the usage of these things. So in next year or in the coming years, if you generate a source of zeptoseconds or even shorter, guaranteed you would also get a Nobel Prize.
वो तुम पे छोड़ता हूँ मैं मधु. तुम जनरेट करो ज़ेप्टोसेकंड, हम तुम्हारे साथ हैं. No, but seriously, this, I mean, so much of engineering would be needed in this, right?
Right. But it's not actually the job of an engineer. It's our job as physicists to fundamentally explain, ठीक है, ये करने से ये होगा. Now, if you explain it effectively, it then becomes the engineer's job. But once you, to all the potential researchers who want to become researchers, I would say when you get into a lab like this, there is no separation like engineer or scientist or PhD student. You would have to become everything.
Yes.
And then only you would be able to do your things on time.
Especially in optics research, I guess everybody has to have some engineering aspect. वो तो रखना ही पड़ेगा. आपको डिजाइनिंग भी करना है, आपको पता होना चाहिए how to do this CAD drawings, how to simulate your experimental setup. This is very important. I mean,
but please don't limit yourself to CAD drawing and anything, because in our lab we are the electricians, we are the electronics people, we are the plumbers, we are the civil maintenance. We do everything in our lab.
I mean, vacuum is a very important aspect in your field, I guess. And according to me, vacuum technology is just glorified plumbing. I mean, you have to do everything like that only. वो nut fit करना है, सारा Teflon लगाना है, पूरा बंद करना है. So it is exactly, for me, it is glorified plumbing actually.
It definitely is glorified plumbing, but you see the scale of this glory.
Precision,
yes. It is. We get vacuums in the order of 10 power minus 11 millibar. You find this vacuum in outer space. So you're doing you're doing plumbing for outer space.
Yes. Yes, great. So yes, actually we have to do all the jobs, and I mean, मैं क्यों ये करूँ, मैं क्यों टेक्नोलॉजी करूँ, मैं क्यों इंजीनियरिंग करूँ, मैंने तो साइंसेस लिया है. ऐसा नहीं रखना चाहिए. We should definitely do everything, and this only develops us as better researchers basically. So yeah, coming back to the topic. So Nobel laureates का हम डिस्कस कर रहे थे क्या क्या था. उसमें हुलियर का I mean क्या बोल रहे थे, फिर से थोड़ा सा.
उनका जो कंट्रीब्यूशन था वो थियोरी को समझने के लिए they were able to explain what attosecond trains are and how to generate them, how to generate single attosecond trains. Okay. So ये process था. So I can't say कि इन्होंने ये किया है, because in our division we can't, in our area of research we can't write single author papers. Nobody can do, only theorists can do single author work in our area.
Experimental involved होता है कि सबको, I mean everybody's expertise is needed, right?
Definitely, it's not just the expertise. The lab is so huge that one person can't do so many things.
Yes, I think so. Sommelier has some questions. Yes, please, Sommelier, please ask.
Yeah, in the talk which I was telling, it's really an insightful talk. But being a biologist, connect it with it becoming very. I don't know how to explain. I'm not able to correct. So can you please, that electrons means how you're telling about attosecond electrons in a very simple manner? If you can tell it once more, it would be great.
Okay, so थोड़ा basics Madhu about मतलब ये attosecond और इलेक्ट्रॉन का क्या लेना देना है, एटोसेकेंड क्या होता है उससे पहले देखते हैं. लेट्स टेल देम अगेन. मतलब एटोसेकेंड क्या है एंड व्हाई इलेक्ट्रॉन एंड एटोसेकेंड आर रिलेटेड.
Okay. If
See, atto, I mean, that is 10 is to minus 18.
Yes, that is 10 raised to minus 18 seconds per million.
right. So
Yeah, that I know. But what? Yeah, please carry on.
आपका आवाज कट रहा है सौमिल्य.
Yeah, I know you got my question that then I'm not able to connect. Being a biologist, I'm not able to connect what is to tell.
okay.
It would be great if you can simplify it.
Okay. So see, let me talk about femtosecond first. So 10 power minus 15. The vision that is happening, rhodopsin जो आंखों में होता है, the rods and cones में जो rhodopsin molecule होता है to identify the colors. That the rhodopsin molecule will polymerize into different structures in the presence of different colors. And this polymerization that is happening is of the order of femtoseconds. Now, in 2005, a group of researchers studied this. They wanted to see how fast does our biology, does our rhodopsin molecule reacts to the light that we are receiving. So, in biological aspects, femtosecond and attosecond is equally important. Now, see, attosecond में you can say that electron travel हो रहा है, how are a biologist facilitated और वो biologist को कैसे use हो रहा है. Now, I don't know exactly क्या होता है, but I have seen long chain, what do you say, long chain proteins या long chain biological compounds. So, इसमें क्या होता है, एक्टिव साइट्स जो होता है where another molecule will come and interface with that. These things are responsible for different biological process. How are these active sites created? There is a charge deficiency or charge proficiency there. There is an increased positive charge or a negative charge. Now, in sometimes what happens, this charge migrates from one place to another. So the active site will shift from one place to another place. Now, when this shift happens, the other molecule which is connecting with this will go and sit in another site, which will cause some other effect. So to study this, you need an instrument which operates, or you need a scale of attoseconds. Kyunki jo electron travel ho raha hai, it is in the scale of attoseconds. To effectively understand how this is happening, we need attosecond sizes. Biologically, I'm a little handicapped क्योंकि मैंने biology 12th में छोड़ दिया. But from the talks that I have heard in my area, photosynthesis and different types of chlorophyll interaction in photosynthesis, all of this happen in the order of femtoseconds to attoseconds. So to understand these, we need attosecond size. Now you might ask me, okay, so what? We know this is going to happen. So why do we have to understand this? Now I'll give you a very oversimplified example. Now, you have sneezing or you have cough. You take a tablet which is for cough, but you get a headache for that. That is called a side effect. Why is this happening? Because it is yielding some other product which is not required. But if A is the current state and Z is the cured state, and A to Z के बीच में एक reaction pathway बन रहा है. Now, if I know how this reaction goes from A to Z exactly, I will be able to trim this pathway. I will be able to focus the reaction pathway to go from A to Z without any side effects. So this is not only limited to pharmaceutical industry. This is plants may, there will be, if you give some sort of fertilizers, there will be another reaction. उसको कैसे trim down करना है, or in rocket science, if they are yielding pollutants, how to avoid that. These are the different ways in which attosecond chemistry can help. But now if you ask me what is the application of attosecond industry to biology, it is very difficult for me to answer that question, because we need more integration of biologists with the labs that we have to find out where else can we find the what application of this.
Yes. So basically, हमको एक
Yeah.
हाँ familiar. Yes.
Yeah, what I can understand from your talk means, suppose two molecules are there, at what particular rate they are binding, that we are trying to understand. And they are binding electron, the electron density cloud is different, shifting in attoseconds level.
Yes. You were right on the last part, wherein you said the electron cloud is traveling in the order of attoseconds. अगर दो reactions बन रहा है, मतलब एक molecule ये path choose कर रहा है या ये path choose कर रहा है, it is defined by the electron cloud. वो electron cloud attosecond में shift हो रहा है. वो electron cloud अगर यहाँ पे तो ये बनेगा, यहाँ पे है तो ये बनेगा. This is guided or measured using in attoseconds.
Okay. Now I understand. Now I am able to understand it.
Sure.
Thank you.
Yes. So basically, if we know how the electron is moving from A to B to C up till Z, तो हमको अगर वो पता है तो हम उसको कंट्रोल भी कर सकते हैं. नहीं तू A to B नहीं जा, तू A to C जा, G पे नहीं जाना है तेरे को, सीधा H पे जाना है, right? So we can control that, and hence that is very important in all the aspects of our life, I think so. हमको जो भी unwanted चीजें लगता है वो हम eliminate कर सकते हैं using this. So future में बहुत कुछ हो सकता है इसकी वजह से. I mean, there are vast potential is very vast, I think.
Right. I would always give this example. Nobody knew when they discovered semiconductor it could be in the palms of your phone.
Yes, true, very true. जब इलेक्ट्रॉन डिस्कवर हुआ था तब किसी को नहीं पता होगा कि इतना उसका यूज होगा. I mean, it is everywhere, the electricity and the semiconductor ICs everywhere. So yeah, very true. So fundamental science should never be ignored, and this is a big wake up call for India also, जो अभी बहुत applicative research में ही mostly वो funding दे रहा है, right? So that is there. Okay. So in this race of generating and detecting the shortest pulses, has someone gone below attosecond, और किसी के पास मतलब किसने सबसे छोटा पल्स बनाया है? Who has made the shortest pulse of light?
This has been documented in the Guinness Book of World Records. 43 attoseconds का एक Swiss group है, which is दो लोग उसमें involved है, हांस येकोब वार्नर करके और थॉमस ग्वामिट्स करके, उनका टीम ने बनाया है. So this is 43 attoseconds long. The pulse was 43 attoseconds long.
Okay. और जनरली कितने attoseconds का बनता है? ये जो नोबेल लॉरेट्स बनाया है, what is the time frame of their pulse?
Okay, the time scale of ये Pierre Agostini का जो seminal paper है, in that they have seen at 260 attoseconds pulse duration वाला pulse. So you see, saying अरे typically कितना बनता है, it's not the right way to look at it. Because there is something called phase mismatch.
Okay.
So ये fundamental pulse, ये जो pulse light बनाने के लिए you need multiple frequencies. वो multiple frequencies का जो crest है, सब एक जगह पे match होगा तो best pulse मिलेगा तुझे. This is called the Fourier limit. But now if you keep separating, even this is a pulse laser, this is also a pulse, but iska jo agar if you track the time duration, it is larger compared to this.
Yes, great. And coming towards the end of my questions at least, तो भाई attosecond तक पहुंच गए. अभी 10⁻⁻21 seconds, that is zeptosecond, उसका क्या मतलब फ्यूचर लग रहा है? What are we going to make this pulse? क्या लगता है आपको?
I can never say that we are not going to make this pulse. We definitely will, but we just don't know how we are going to do it, or at least it's a wrong statement. I don't know how we are going to do it. So recently there was a paper in which they have studied a molecule in the order of zeptoseconds.
Yes.
So in that sense, we know that there is a scale called zeptoseconds, and we know that is going to happen. If you ask me, my thought would be to do something with the nucleus.
Yes.
You use a laser, you stimulate the protons and neutrons, and from that you might be able to produce zeptoseconds. This is still a theory in making.
Okay, so we know that neutrons are very heavier than protons, right? And of course they are chargeless. So to stimulate them is very difficult, I think so.
Of course it is difficult. Then we'll have to look at what are inside that. There are quarks inside that. We will have to stimulate those things.
Oh my god. Itna chota. How are we going to do it?
We'll see.
Yes.
If we are alive for another 50, 60 years, we will definitely see that.
Okay, this is great. I mean, the future looks very bright. And I mean, if we are able to make zeptosecond pulses, okay, yeah. So Somilia has another question. Yes, Somilia.
Carry on. Afterwards, I will talk about it. You can carry on.
Okay, sure. So zeptoseconds, if we make such pulses, so we are going to study the nucleus, and we can control the nucleus of an atom using it. So the nucleus is related to nuclear reaction, the radioactivity. So am I wrong to say that we can control nuclear reactions or radioactivity using zeptosecond pulses?
It's a very... I feel this is not a very focused question because already we are controlling nuclear reactions, which is called a nuclear reactor.
Okay.
Uncontrolled nuclear reaction is called a bomb. Now, if you are asking me, can we somehow make a nitrogen atom using from an oxygen atom?
Yes, maybe. Yes.
एक न्यूट्रॉन को वहां से लेके आके यहाँ से डाल देना. These things, I wouldn't put it past. It is definitely possible. If you are able to control it, or if you are able to study it, you can definitely do this. And I think we are using the word control very loosely here, because it is not as if picking a phone or picking up a pencil. It's not that easy to control. So in our lab, in my experiment, what I had to do is I had to get a stage which moves in the order of nanometer. Its resolution was 5 nanometer.
That is really small.
The width of your hair is 200 nanometer.
Yes.
That is what? Almost 1 million times smaller than that.
Yes.
So in that small scale, you need to operate these things. For that, you need a lab wherein it is isolated from everything. So this control word,
vibrations and seismic vibrations also, I think so.
Right. This control word shouldn't be thrown very easily, because it is very difficult to already control this. Now you are speaking of making some other atom or some other thing in the nucleus, which is even more difficult. So I don't want to comment a lot more, because this will become science fiction.
Yes.
It won't stay science anymore.
Okay, sure, Madhu. So I come to the end of my questions now. If the audience has any questions, then we can take it up, starting from Somilia. So he had raised an hand. So please, Somilia, go ahead.
Yeah. Hello. One more question I have. So we have to know that the electrons that shift in electron cloud shift in 88 for attoseconds. So since the research with Nobel Prize, it's been very great research, but I don't know how it is going to be applied in various fields. So can you tell the application of this particular thing? Where will it be applied, or will it be for its kind of basic research?
Yes, this is actually a fundamental discovery. You can't see any application of this currently. So higher harmonic generation jo hai, there you generate XUV pulses, wherein it has been theorized this can be used in the manufacturing of silicons, the chips and everything. But currently I don't see any application of attosecond sciences. But as I said before only, like nobody knew when the semiconductor was introduced it would be put into your mobile phones. So maybe in the future some of the researchers or some of the engineers might come together and find applications for this. Currently I don't see any application in femtosecond pulses other than understanding the molecule.
What I feel, something according to my gut feeling, I feel it can be used in better microscopy.
Oh yes, that is called attosecond microscopy. So in microscopy also there are two things, right? It is spatial microscopy or temporal microscopy. In temporal microscopy, there is already femtosecond transient absorption spectroscopy, or that is also sort of temporal microscopy. In similar way, you can do attosecond microscopy. So, but until now, in attosecond sciences, from what I have learned, it is only very huge molecules. Proteins tak kabhi gaye nahi hai. We have to go to proteins or we have to go to complicated biological structures, then we will be able to see real life applications.
But we can go. Nothing.
Definitely. I'm not saying we can't. Definitely we can go. Now, actually, to expand on your question, I would ask, kis phase mein ye ho raha hai? Until now, the attosecond generation or higher harmonic generation is only happening in gas phase. Now, abhi solid phase mein shuru hua hai. Now, if you do it in solid phase, it is very easy to put proteins in that path and interact with them. But proteins को aerosolize करके study करना comparatively मुश्किल है.
Yeah.
So we are heading in the right
so
direction.
Is it possible if at microscope developed, we can study the proteins in liquid form as well?
Definitely. We are already, see, liquid is in between gas and solids. Liquids को usually, even in our lab, we study some liquids. हम क्या करते हैं उसको aerosolize कर देते हैं. So when you reduce the ambient pressure to almost 10 power minus 7 or 10 power minus 11, whatever liquid is there, it will become into gas phase. वहाँ पे चला जाता है. Now, I'm telling you, we are already in the regime wherein we are studying solid state higher harmonic generation. Actually, interestingly, that will be my next postdoc as well. That is what I will be working on. So मैं बोल रहा हूँ अभी gases का हो गया, solids का हो गया, definitely liquids का भी हो जाएगा.
Thank you so much. Really, thank you. And really thank you for giving your time to us.
No problem.
Yeah. So any more questions from the audience? Okay, so I guess this is the end of our science chat today. So Soumilya here has shared a link. I think so. Yes, Soumilya, please.
That is the feedback form of this current SciChat. Please do know. Until then, think, share, and let us know what you want from us, that from the SciComm synapses, so that we can organize more such intriguing talks and events.
Yes. So please fill up this feedback form, everybody. Madhu, तुम भी fill कर देना कैसा लगा experience भी, है ना? So it has been a wonderful chat with you. Sunday सुधर गया मेरा, है ना? मजा आ गया. So we will have another SciChat afterwards. We will keep the audience in loop for this, and please everybody join for the next sessions also. Till then, have a great Sunday and have a great week ahead. Thank you, everybody. Thanks, Madhu.
Thank you. Thank you for this opportunity.
Yeah. Bye.
Bye.
Thank you.